We'll try to revisit this root locus. It's a very important part. It will be a very significant part of your project. So, what you're seeing here is the basic, is for sketching a basic root locus. Are you able to see it? We need the board as well. So, see, these are the basic rules for sketching a root locus. Okay. All right, let's do this. So we'll continue, and as we go through, I'll explain to you the example again, how to do it. Let me start by saying we're going to discuss how to refine root locus. The example we're going to talk about is k into s minus 3, s minus 5. S plus 1 into S plus 2. All right. So again, the goal is sketch root locus to determine or design a value, let's say range for k. Okay. So you're given the system and you're required to figure out, you're required to suggest a value for k. Okay. As a design engineer, you're required to suggest value for k. So how do you go about doing that? So the first thing you'll do is you start following these rules. So the zeros here are, let's say, poles. What are the poles of open loop system? Poles are S equal to -1 and S equal to -2. Similarly, zeros of open loop system, 1 is 3 and Z2 is 5. Okay. So as shown here, the first thing we do is we calculate sigma A. Okay. Sigma A is called the real axis intercept, and sigma A is given by summation of, you see here, summation of finite poles minus summation of finite zeros divided by number of finite poles minus number of finite zeros. Okay. So if you look at summation of finite poles, it is -1, -2, which is -3, divided by, -3 -8 divided by divided by 0. So this is actually infinity. Okay. And theta A, these are the asymptotes. Theta A is generally given by 2k plus, 2k plus 1 into pi over, again, summation of, number of finite poles minus number of finite zeros. This is also infinity. Huh? This one? Huh? It's summation of finite poles minus summation of finite zeros divided by number of finite poles minus number of finite zeros. Okay. All right. So this is what you figure out. So when you start sketching, this is how you start sketching. The first step is always to do this. And the next step one, two, three, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay. So where are your open loop zeros? Open loop zeros are you have 1 at plus 3, so it is 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, 4, minus 5, okay. This is one of your zeros, and this is the other 0. And your poles are this one and this one. If you look at the first point, not the first point, let's say, yeah, if you look at the first point says number of branches is equal to number of closed loop poles, okay. So you'll see that there are 2 branches for the root locus, and if you look at number 4, root locus starts at finite and infinite poles and ends at finite or infinite zeros. You have to understand something here. Every branch of a root locus starts from a pole and ends at a 0, okay. So in this example, for example, how many zeros do you see? 1 0. And how many poles are there? There are 4 poles. It's S into S plus 1 into S plus 2 into S plus 4. 4 poles, okay. So you have 1 0 and 4 poles. That means you need 3 more infinite zeros, okay. So, but in this case, you don't need infinite zeros. You have 2 poles, you have 2 zeros. So what you can do is you can start with 1 pole and end at the other, okay. There is something called breakaway point, okay. Let's discuss this breakaway point. See, what is breakaway points? You have to understand. So in this, now let's say you're an expert, or if you do basic root locus plotting without really worrying about the breakaway or the break-in point, okay? You'll sketch it like this. Your root locus will look something like this. This is the root locus. This is how it will look. So it started from one pole. You see two branches here? Two branches of the root locus. This is the first branch. It started at this pole and it ended at this 0. Okay? And the second branch is, it started at this pole and it ended at this. Okay. Now you can do this as well. Yeah. The locus will remain the same. It will not change. Right? This path will not change. The locus will not change. Even if you do this, the locus will not change. So this, but what you need to know is, we need something called a break away point. So here, what is happening is, this is the start point, right? They come like this, and they break away. They break away. Okay? And here, they break in. Right? So you need something called breakaway point and break-in point. And you can precisely calculate what this breakaway and break-in points are. Okay? Now, when you get comfortable with drawing root locus, if you practice enough, you can draw this root locus just looking at the open loop poles and zeros, always. Okay. So for example, if you look at whether we satisfy all of those, the first one is number of branches. The number of branches is equal to number of open loop poles. So there are 2 poles, 2 branches. The first one is satisfied. The second one is root locus is symmetrical about the real axis. So this is the real axis, right? Is it symmetrical about? It is symmetrical, right? About the real axis on the top and the bottom. This is actually a circle. So this is symmetrical. The third one is on the real axis for k greater than 0, the real axis, the root locus exists to the left of an odd number of poles and zeros. So this means this is your real axis, right? If you look at this, why does root locus not exist here? Exist. Why did I just join like this? Huh? It would be symmetrical if I just join this. I can just join that as well. Or I could have done this, right? I could have done this and this. It would still be symmetrical. So what it says is the third one says you start from the rightmost. Okay? You start from the right. Where is the first pole or 0? This is the first pole or 0, right? So root locus will exist on the real axis only. We are talking about the real axis part. Between the first and second, the root locus will exist. Okay? But not between second and third. It says odd number of root locus exists to the left of odd number of poles and zeros. So if you look at this, to the left, until this point, there are odd number of, there's just 1 0, which is odd number. But after this point, there are even number of zeros, right? 1 and 2. So from this point to this point, there are even number of zeros. Huh? Then it will exist between 1 and 2 and nothing else. So if it was just 1, 4 and 1, 0, I would just join this, nothing else. The number of zeros and poles combined. It should be an odd number. Odd number of zeros and poles combined. One. 1, 0. So if you look at this, between this point and this point, to the right, there is just 1, 0. Between this point, there are 2 zeros. So root locus cannot exist in this real part. Again, between this point and this point, there are 3 zeros and poles. 1, 2, 3. So root locus can exist. Now again, root locus will not exist between in this part because there are even number of zeros and poles. That is the third one. Fourth one is root locus starts at finite and infinite. That we already are seeing here, right? It is starting at a finite pole and ending at a finite zero. Okay. The fifth one is, now here we don't encounter asymptotes. Okay. We don't need asymptotes. But if there are asymptotes, for example, in this system, these are the asymptotes. So how do you calculate asymptotes? You just do 2k plus 1 into pi. So for k equal to 0, what is this asymptote? It is pi by 3. For k equal to 1, it is pi. For k equal to 2, it is 5 pi by 3. If there were asymptotes, the root locus would be, what are asymptotes? The root locus approaches straight lines as asymptotes. So what it means is, so if we had another, these are the angles, let's say this is pi by 3, right? So your root locus would be something like this. It would not parallel, it would be asymptote. It would meet this line at infinity. It would meet this line at infinity. It will always get close, 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 but it will never touch it. So these two are asymptotes. Okay. So breakaway points, we need to figure out breakaway points. Okay. Now what is k? For all points along the root locus, this has to be equal to -1. Okay. We actually have covered this. I have shown you why this is the case. So you can go back and look why this is the case. Okay. So if this has to be equal to -1 on the real axis, S should be equal to sigma. Okay. Just to refresh your memory, so what is the closed loop transfer function for this? T of S should be equal to K into S minus 3 over S minus 5 into 1 plus K into S minus 3 over S minus 5, right? S plus 2, S plus 1 into S minus. That's it, correct? Right. So what this means is, so what you're trying to do here is, you can write this like this, correct? 1 plus K into S minus 3 into S minus 5 over S plus 1 into S plus 2. Huh? Top will change. It will be S plus 1 into S plus 2. Right? So what it means, it simply means, this simply means the poles, these are poles, right? All these paths are actually poles for different values of K. Just like these are poles, right? How do we figure out the poles of this open loop system without the K? You equate this to 0. So similarly, you equate the denominator to 0. If you equate this denominator to 0, you're going to get this. So you move 1 on the other side, you're going to just get this. So for all points along the root locus, this has to be 0 for different values of K. Okay? So on the real axis, what happens is, this S will just have a real part. It will not have an imaginary part. So it is just that sigma. Sigma is, it means just it will have a real part. There is no imaginary part. So for anything other than, if it's not on real axis, then it will be sigma plus j omega. Okay. So substitute S equal to sigma in so let's call this A. In A, you're going to get K is equal to minus S square plus 3s plus 2 over square minus 8s plus 15. Okay. So I just took this, substituted s equal to sigma, and moved this around. Okay. So this comes to the numerator, this comes to the denominator. All right. Now you have to understand that if you do a dk by ds, all right, which is 11 sigma square minus 26 sigma minus 61 over s square minus 8s 15, and equate this to 0. K by d sigma. See, at this breakaway point and break-in point, you'll find that K is the maximum or minimum at this point. Okay, and how do you figure out maximum, max, min? You differentiate that and equate it to 0. I think you should know this by now. But it simply means, see, you have to think about it like this. You look at this curve. Okay. Yeah. So if you look at this curve, where is the maximum value of K? Huh? Huh? Right. I substituted s equal to sigma. Okay. In this one? Oh yeah, you're right. It is sigma square. Sorry. If you look at this curve, where is the maximum value of K? Right. This is the maximum value of K, right? See, what it means is when you have a curve like this, at the maximum, what is differentiation? Differentiation is, what you do is, you take the value of K at two different values of sigma, and just, you think about it as just, so the differentiation between this one and this one, it's just value higher minus value lower. Okay. Whenever it is at the maximum, the differentiation is 0, because the maximum and minimum are pretty much the same. And it is the case for minimum as well. Okay? So if you do a K sigma, wherever the value of K is minimum, you differentiate the value of this is, what is this? This is K as a function of sigma, how you read it. Okay? So when you differentiate K, and you equate it to 0, at that value, it is either maximum or minimum. This is always the case. Okay? So if you do this, you're going to get 11 sigma square minus 26 sigma minus 61 is equal to 0. Okay? And if you just solve for sigma, you're going to get sigma is equal to, there are going to be two values for sigma, minus 1.45 and 3.28. Sorry. Okay. So point is sigma equal to minus 1.45 and okay. So what you need to really take from this is, you take this, figure out the breakaway and break-in point, substitute S equal to sigma in this, differentiate it and equate it to 0, you'll get a quadratic equation. And all you need to do is figure out the roots of that quadratic equation. You'll find two roots, and it is very convenient, or it is common sense, right? If it is, so breakaway point has to be between these two. Do you see this minus 1.45 lying between these two? So that has to be the breakaway point. Break-in has to be between these two. Do you see this point as lying between these two? That is the break-in point. Okay. All right. I think we'll discuss a little bit about the lab and your project. If you don't want your project, we can have just a final exam, and all your points will be based on your final exam. We want a project. Okay. Huh? No, this course. Hmm? It is individual project, yes. Hmm? Yes, I can go over the project. So your project, um, the project is already up on Blackboard. So what you need to do is, there is going to be there's a spring mass damper system in the lab. Okay. You need to, first of all, you need to make up for the lost, for the labs you have missed. You need to do at least 3 more experiments on that machine. Okay. So what you have over there is a spring mass damper system. You know what a spring mass damper system is now, is by now. Each one of you will have to design a configuration of your spring mass damper system. The spring mass damper system over there has many masses. So there are 3 masses, or 3 there is provision to have 3 masses, and between each mass there are springs, and there is 1 damper. Okay. Now what you need to do is, you need to figure out your configuration, all the 3 components. Okay. You need to figure out your configuration. There are these masses will be different. So there is a carriage which will carry each mass, and you can add mass, you can subtract mass to those. So build your configuration and show me what configuration you are going to work. Okay? Each one of you has to do this. You have to, either through manual or by measuring, by actual measurement, you have to figure out what is the exact mass of your configuration. Each this thing. There will be a spring constant. You have to figure out what the spring constant is. There's a damping system. You need to figure out what's the damping coefficient of the damper. Okay. Once you have done with that, you essentially follow what is on Blackboard. Okay. For that, one of the things you should do is start with system identification lab, which is today. Okay. The final and the project both are, the initial this thing was you do the project and the final would be the split between your project and the exam, the comprehensive exam. The final is 40%, yes. I think so. Now, you'll not be given an option individually. If you want to take final, then all of you have to take the final. Skip the project. And if you're going to do the project, all of you have to do the project. So you guys want to do a project or you want to do a final? Or both? There is no or for final comprehensive exam, so it will be? So just the final project or both? So just the final exam or both? Comprehensive exam or both? Hmm? Once you have set up the system, most of it is really easy. Okay. You may want to do Simulink to do your spring mass damper system. You can use MATLAB. You need to show. You may have to do root locus. Again, root locus is also very simple if you do it in MATLAB. Okay. So project and final exam. The project will be due before the final exam. 12th of December. Okay. So it will be due before that. All right. We'll discuss it. We'll discuss it in the lab session today. I'll show you exactly what we are talking about. Make sure you just go through what has been uploaded on Black.